So we are discussing chemical bonding, and in the previous sessions we have taken up covalent bonding. And the first worry when we are taking up the covalent bond is basically, where does the strength of the covalent bond come from? That is the biggest worry we started off when we were discussing what covalent bond. And to address that difficulty in understanding where does the strength of the covalent bond comes from, then came the valence bond theory proposed by Linus Pauling. And we were able to explain the strength of the covalent bond is derived by the extent of overlapping of atomic orbitals. So the concept of overlapping has addressed the concern, where does the strength of the covalent bond come from, right? That has been addressed. Now the issue is, when we propose valence bond theory, we are very excited because, there was no theory which can beautifully explain the covalent bonds that are present between two atoms only, that is diatomic molecules. There is absolutely no theory which can better explain diatomic molecules. There is absolutely nothing available. So we are very happy when we are dealing with the valence bond theory. And suddenly what happened is, in case you shift from diatomic to triatomic, the bond angle kicks in. The bond angles kicks in. And now when the bond angles are kicking in, you must be in a position to explain those bond angles. You must be present a theory which will back the bond angles, the structures of these bond angles. So when we were applying this valence bond theory to a triatomic molecules, then I think we see some silly things of the Linus Pauling, and in fact ridiculous things also, I would like to say, because he is completely flawed is the theory of the valence bond theory, as well as, when you apply it to triatomic or tetraatomic or in fact polyatomic molecules, he not only failed but miserably failed. So it has a limited things. We could not cover as many molecules as possible as well as valence bond theories are concerned. So we restricted ourselves to only diatomic molecules, and we could not extend it toward triatomic or polyatomic molecules in that case, right? The other one, which sounds ridiculous, is basically, before this proposal of valence bond theory, we were thinking that the atoms are approaching one another and one atom is overlapping with the other. One atom is not overlapping with the other. In fact, if you have a micro details that were given in the valence bond theory, it is not the atoms that are overlapping. Rather, it is the orbitals in that atom, one atom, and the orbitals in the other atom, they overlap. And this overlapped orbital is actually holding these two atoms together. That's what is the concept, but not the atoms overlapping with one another. That's ridiculous. So that point is also addressed, right? The strength of the bond, covalent bond, where is it derived from, has been addressed. The shapes of the diatomic molecules are beautifully explained. But coming to the polyatomic molecules, more than three atoms, the bond angle kicks in, and we could not explain those bond angles. That's number one biggest drawback of the valence bond theory. The second thing is, whenever p orbital is projected onto S, its direction is not fixed, the bond angles are not fixed. When the bond angles are not fixed, I think we are not in a position to determine the structures of such compounds. That is another problem. The most ridiculous part of valence bond theory is, whenever p orbitals are involved, the bond angle remains to be absolutely 90, which is nonsense, because you are telling me that the fifth group hydrides, that is ammonia, PH3, and ASH3, SBH3, right, all BiH3, all will be having the similar bond angles, that is 90 degrees. And not only fifth group, if you compare it with the sixth group, you have H2O, water, all these compounds will be having bond angle 90, which is not the case. So it is ridiculous to say whenever p orbitals are involved, the bond angle remains to be 90 is a serious flaw. It's not only a serious flaw, it's silly, it's nonsense rather. In fact, it is ridiculous, because the bond angles are varying from each and every compound. That we need to address. So these drawbacks of the valence bond theory formed the basis for explaining another theory, that is hybridization, you must understand, right? So these serious drawbacks have laid the foundation for search for another theory which will explain all these things, right? So remember that when we propose any theory, right, they are not methods of preparations of compounds. Remember that. These are not methods of preparations of compounds, whether it is a valence bond theory or the hybridization or valence shell electron pair repulsion theory. These are absolutely not methods of preparations of the compounds. The compounds are already there. We should have a theory which backs them, right? So in that process, to explain why a p orbital projection onto S is absolutely not fixed, and we are not in a position to determine bond angles of polyatomic molecules, then I proposed a theory which is hybridization. I was telling you, right? Hybridization, and it is intermixing of atomic orbitals within the atom to generate entirely a new set of orbitals. That's nothing but what? Hybrid orbitals with better directional properties. With better directional properties. That means that before bonding itself, everything is fixed. So before bonding itself, everything is fixed, the bond angle is fixed, the structure is fixed, and everything is fixed, right? So we don't have the last minute nuisance of which way to come, acute, obtuse, or whatever, as we struggled in the case of what valence bond theory. So we were very happy explaining some of the structures through what hybridization. But what, as I said, whether everyone have merits or not, we don't know, but I'm sure that everyone will be having demerits, as the case of hybridization also. So valence bond theory covered some compounds, diatomic molecules. Hybridization has taken over, right? And it has covered some more compounds. And then it has, again, drawbacks, you must understand. Now, why it has drawbacks? Because remember that hybridization completely ignored. It completely ignores the presence of lone pairs and their influence on the bond angles. So that seems to be absolutely silly, because what happens is when the two atoms are approaching one another, each and every electron in these two atoms get influenced when you get closer, right? And the case of valence electrons are much higher. So hybridization ignores the presence of lone pair on the central atom. When you ignore, it will have some influence, and I can tell you that each lone pair actually has an influence of 2.5 degrees on the bond angle. So if a central atom has one lone pair, and if you are ignoring it, then the actual bond angle must be cut by minus 2.5. You must understand that, right? 2.5 is significant, and you can't discount it. And imagine you have two lone pairs. When you have two lone pairs, almost 5 degrees is cut from the expected bond angle. So 5 degrees cutting from the expected bond angle is seem to be significant, where you cannot discount it. Similarly, 3 bond angles, so 3 lone pairs, 4 lone pairs, 5 lone pairs if you have in a compound, and hybridization starts to ignore it, which is, I think, will be having an effect on what? The bond angles, and of course the structures get distorted. That is the issue which is concerning with what? Hybridization, you must understand. That we have noticed it. So hybridization exclusively, beautifully, convincingly, whatever words you can use it, it is best suited for compounds in which the central atom has absolutely no lone pair. It exclusively has bond pairs. There are no lone pairs on it, right? If you have lone pairs, then I think we have to search for another theory, and we were searching for that, and that's nothing but the valence shell electron pair repulsion theory. So from now onwards, as a science student, as a chemistry student, you must understand the shape of the molecule basically is determined by both lone pairs as well as what? Bond pairs. You must understand that. So the shape of the molecule is determined by both lone pairs and bond pairs. If I tell you correctly, then the shape of the molecule is determined by the number of lone pairs and number of what? Bond pairs. Right? It is the number which matters. It is the number which matters. You must understand. Right? I gave you a list where, you know, the number of lone pairs and number of bond pairs will determine the shape. And the student is supposed to go through that in the previous sessions and remember, right? Now coming to the other point, that is now we will discuss about the concept of what? Dipole moment, and I would like to introduce it to you. So let us understand what is dipole moment, why it is creeping in, and what is the necessity of it, right? And here is what is the briefing is. Remember, in covalent bond, look here, in covalent bonding, so we are still in covalent bonding. We are still at the covalent bonding. What we have done is, covalent bond, everyone has an idea, you know, everyone has an idea, you give one, I give one, we both achieve octet by sharing a bond pair. That is a perception what we have, right? The strength of the bond is derived by the concept of overlapping proposed by theories. Now what I'm telling is we are still hanging on to covalent bond, and in covalent bonding, I think you have two systems. One is a homoatomic system, the other is an heteroatomic system. In homoatomic system, the shared pair is absolutely at the center. And in the heteroatomic system, I think the bond pair is unequally shared and it is towards that atom which is small. Well, I would like to repeat what I'm telling. I draw the attention of everyone, please. We are still in covalent bonding. What I'm telling is the shared pair, if it's at the center, such a situation will arise when the two atoms which are sharing these bond pairs are similar. Then the shared pair is exactly at this center, right? And suppose if it is a different atom, the only difference between two different atoms in chemistry is absolutely size. So if you take two different atoms, one of them will be small. And the smaller ones attract more. That is what is told in chemistry. Smaller ones attract more. So if you take two different atoms, one of them will be small and the bond pair is close towards that atom which is smaller. So I can simply say you have unequal sharing of what? Bond pair. You basically have unequal sharing of bond pair. When you have unequal sharing of bond pair, then poles develop. When poles develop, I think there is something to measure into it. There is absolutely something to measure into it, you must understand. Right? In homoatomic system, there is absolutely nothing to measure. For example, look here. You have two systems. One is the homoatomic system. This is the homoatomic system where you have two similar atoms. Same, A and A, both are similar. And if they are participating in covalent bonding, the shared pair will be exactly at the center. So you can actually see this is equal sharing of bond pair. Equal sharing of bond pair. So I have nothing to measure here. I can simply say, yes, these two have participated in bonding, and then the shared pair is exactly at the center and both are sharing equally. That's what it is. You can see that and just check it and enjoy. There is absolutely nothing to measure. What is that you're going to measure? There is absolutely nothing in it. A has given one, the A is another A has given one. We both put it at the center. We live happily and the covalent bond is established, right? Now in case of heteroatomic system, which I'm writing now, watch carefully here. Suppose if it is heteroatomic system, watch. It is heteroatomic system. In heteroatomic system, where you have A and B, this is a bond between A and B. And when we say, what is the difference between 130 elements in the periodic table, if someone is asking me, you have 130 odd elements in the periodic table, if someone is asking me what is the difference, I simply say it is size. Other than size, there is absolutely nothing. Because every periodic function, what we have discussed, is a function of what? Size. Everything is about size. So in heteroatomic system, you have two different atoms. One of them will be smaller. Assume that B is small. This is small in size. This is small in size, and we were told smaller ones attract more. The smaller ones attract more. This attracting tendency is referred to as electronegativity. This is referred to as electronegativity. And when the atom is smaller, I think it has more electronegative. And then what happens is this bond pair is basically pulled towards that side. So you can actually see here you have unequal sharing of bond pair. Unequal sharing of bond pair you have. You have unequal sharing of bond pair. When you have unequal sharing of bond pairs, then what happens is poles develop. Poles develop. Now what is happening? The shared pair which is supposed to be at the center is shifting towards this side. So you partially gained it. This is a partial negative charge. Partial. Because you're shifting towards B, you develop a negative charge. That's partial. Why partial? Why partial? Because remember one point, we are discussing covalent bond. When we are discussing covalent bond, A has invested an electron, B has invested an electron. So someone is taking away, is not completely taking away. If you completely take it, it's an ionic bond. I draw the attention of everyone. Please understand, we are discussing covalent bond itself. And very consciously I have put partial negative charge. That means there is a shift of this pair towards B. That's all. When I say shift, the electron invested by A is not leaving its shell. If it leaves its shell, then it's complete ions. Remember that. If it is complete route, then it would have formed A plus and B minus if it is completely gone. This is ionic bond. We are not discussing that at all. We are absolutely not discussing that at all. It's absolutely covalent bond. It's a heteroatomic system. One of the atoms is small. When the atom is small, the bond pair is not at the center. It's pulled towards that atom which is smaller. And smaller ones attract more. So I put a partial negative charge, not complete charge. So when I say partial, it's a fraction of the total charge. You must understand, these things must be understood immediately by the student. You should translate, right? When I say partial charge, this charge might be a fraction of the total charge. What is the total charge? The total charge in case of what? Ionic bonding. If this bond is completely ionic, you would have got the full charge. So that means that this charge which is developed is a fraction of that. You must understand, right? Similarly, when you are pulled, you develop a partial positive. Why partial positive? Because the electron of A remains in A. It's not actually getting out of the shell. It's only a shift. And the shift of electron can be understood only when you think that electron is like a cloud. You can't imagine an electron to be a pepper seed or a mustard seed, and then you do all these things you can't understand. Remember, have some maturity in dreaming about electron. It's like a cloud, and cloud, it has a diffusing property. It always relaxes, and it always shifts, it always migrates, it always diffuses. So in such case, it's easy to understand that this electron cloud of the two bond pair, the bond pair is shifting towards B. So I develop only partial negative charge. The student, when you are listening to me, you understand that this partial positive charge is a fraction of the total positive charge in case AB was ionic. Remember that. Remember, it's not ionic. If we stay with what? Covalent bond, you must understand. So I'm clear, I'm very much clear. You should be smart enough to understand what I'm telling, right? So what I'm discussing is basically we are still with covalent bonding, and we have homoatomic system, and we have heteroatomic system, and there is absolutely nothing to measure in a homoatomic system. It's like a story. What is the story? Like you give one, I give one, we both put it at the center and then enjoy. It's like a story, right? Now there is absolutely nothing to measure. In case of heteroatomic system, what is happening is the shared pair is unequally shared. The bond pair is unequally shared. In case that you have poles developed, these poles are the fraction of the total charges that are available. And since you have poles, I'm forced to actually measure something. There is absolutely something to measure. In case of what? Heteroatomic system. We just can't leave it. It's not like a story, because you have an unequal sharing of what? Bond pair. And this unequal sharing of bond pair is absolutely nothing called, it's absolutely called polarity. So if someone is asking you what is polarity, then you tell him that it is unequal sharing of bond pair, which results in the formation of poles, and hence this phenomena is called what? Polarity, right? So there is something to measure. What is there to measure? Let us now ignore the homoatomic system. It's like a story, and let's take up heteroatomic system and then see what exactly is the dipole moment. Look here, watch. The heteroatomic system. This is what we were discussing. Let there be a bond between A and B. Let B be smaller in size. When you are smaller in size, you actually pull it. So you develop a partial negative charge, and this develops a partial positive charge. So the poles have been developed, right? And remember, when the poles are developed, as I said, in heteroatomic system, there is something to measure. Now, what is something to measure here is, since the poles are developed, and you remember, when I lose one, when someone is gaining one, you're losing one, right? When you're losing one, you gain one. That's what it is. So the magnitude of charge, whether it is positive or negative, would be the same, because it is the same quantity which is pushed towards the other side, right? So there is absolutely something to measure. Now, what is something to measure is this. So the direction also is important, this way. So in fact, I would like to put the direction like this. This way it is pulling. This way it is pulling. And the positive charge should be put on the tail like this. So it's basically a vector quantity. It's vector. So the dipole moment is shown as a vector, and the pull is towards the pull, that is a negative charge, and the tail will be having a positive charge, and the vector is shown like this, right? If this is the case, if this is a, let me rub it off everything and just put the vector to you. This way is the pull, and you have a positive charge on the tail. That is how it is shown, right? Which way is the pull, you can easily identify through the vector. Now what I will do, let the charge developed, let the charge developed be, let the charge developed be what? E. And the charge is E. So the poles have been developed, and let the magnitude of the charge be E. Right? Then I don't say this is E, that is E. Both are E, because we are taking the charge which is developed, not the sign. It's absolutely not the sign. So you can see let the charge developed be C, and let the distance between the charges, let it be D. Let the distance between these two is basically D. The distance between the poles, otherwise we call it to be poles. The distance between the poles, let it be D. Right, let it be D. And the charges are what? E. Then, observe carefully, then the product of E multiplied by the distance. The product, that is E multiplied by the distance. What is E? E is the charge developed in an unequal sharing situation. In a covalent bond, if the bond is unequally shared, the bond pair is unequally shared, charges develop. The charge magnitude that is developed is nothing but E. And the distance between the charges is D, right? Then the product of E into D, the product of E into D is given as mu. That's given as what? Mu. And the mu is basically nothing but this. This is what? This mu is called the dipole moment. This is what is called the dipole moment. You must understand that. That is what is called the dipole moment. Right? So if someone is asking you, a brother or sister, or when you venture out, someone is asking you as a science student, right? Someone is asking, can you explain dipole moment? It's as simple as that. This situation will be arising only in a heteroatomic system in a covalent bond, where the bond pair is unequally shared. When the bond pair is unequally shared, I think the bond pair is towards that atom which is smaller, right? And the charge developed is E, and the distance between the poles is D. The product of E into D is mu, which is called dipole moment. So there is absolutely, it's a common sense that in heteroatomic system there is absolutely something to measure. There is something to measure, which I have done. And the mu is called what? Dipole moment, you must understand. The mu is called dipole moment. Now the other question arises. How to communicate. How to communicate. That is the another issue. Right? So the people will ask me, are they units of dipole moment? Are they units of dipole moment? Do dipole moment have units? How do we communicate? That is another issue. You can't say that I have a bond in my house whose dipole moment is this much. When someone called me and said, I have another molecule whose dipole moment is this much. This much and this much is not the way to communicate. If you have a unit, then I think we will communicate in terms of units, not through gestures. This much, this much, this much. This is not the way. That's not the way. So what we will do is we will devise a unit for it. Right? How do we devise a unit? You must understand. Let us see. Now suppose if you go to a cloth shop, and ask me, give me cloth, will he give? No, absolutely, he doesn't give you. When you go to a cloth shop and ask for cloth, you just can't ask him, give me a cloth. He doesn't give you. He'll ask you a question in reverse. How much do you want? When he asks you how much do you want, you can't show your hand and say this much. That's not the way to communicate. You can't say this much or I want this much. No, you can't do that. Right? There is a way. So you tell him that I wanted 1 meter of cloth. I wanted 1 meter of cloth or half meter of cloth. That's how we communicate. You must understand that. So he has this much cloth, very, very long cloth. He has this much, out of which 100 centimeters is 1 meter. So out of the big cloth what he is having, you must ask him, give me 1 meter. So what is 1 meter? 1 meter is a part of that much cloth what he has. Then that is how we communicate. That is how we communicate with the cloth shop owner, right? Similarly, we have dipole moment. We know what is dipole moment. It happens in heteroatomic system. There is something to measure, and the charge is developed if it is E, and the distance between the charges is D. the product of E into D is absolutely mu, which is called dipole moment, which is called what? Dipole moment. And now the issue arises how to communicate. How to communicate? Shall we show our hands? This much, this much, this much, this much, this much, this much. This is not the way. We are science students. We should have that rational thinking. We should communicate through units, right? So shall we make units of dipole moment? Yes, we can. We can. So as I said, it's a common sense. Out of this much cloth, you're asking me him this much. This much is a unit. And the unit is 1 meter. 1 meter. You must understand. So similarly, what we will do is, we'll actually go in for the units of dipole moment. Look into this. Look into this. How to actually go in for dipole moment units. Units of dipole moment. Let's go into the units of dipole moment. How do we actually calculate the unit such that we can communicate better in terms of units? Because the best way of communication is give me 1 meter, 2 meter, 3 meter, 4 meter, 5 meter, he will give you very quickly. You can't say give us this much, this much, this much, this much. No, that's not the way. So the units of dipole moment, let us calculate it. Now as I said, mu is the dipole moment, which is the product of E into D. This mu itself is called what? Dipole moment. Right? So now we are calculating how to actually go in for a unit. Remember, E is, let E be 10 power minus 10 ESU. Now what is ESU? It's an electrostatic unit, a unit of charge. It's a unit of charge in CGS. It's a unit of charge, electrostatic units. Now people ask me, why did you take 10 power minus 10? Is it your wish? This is a question which is normally asked. Why did you assume E is 10 power minus 10 ESU? Is it your wish? Well, I would like to say yes, my wish. Because I said this E which is bearing a charge, this charge which you put it to be E, is a fraction of the total charge if AB was ionic. That means that this is a covalent bond. Suppose if this bond was ionic, it would have given me full charge. This charge is absolutely full. It's full 1 unit charge. And this E which we are speaking is a fraction of the total charge. This E which we are speaking is a fraction of the total charge. It's fraction of the total charge. It can't exceed the 1 unit. You must understand. So if you ask me, is it your wish? Yes, it's my wish. Provided I don't cross the 1 unit charge, because E will remain to be a fraction. Now why only 10 power minus 10? It is universally taken to be 10 power minus 10. If you wanted to take less than 1 unit charge, you are supposed to take it, you take it, no one will hang you. It's your wish. So suppose if this bond was ionic, the charge is full, and the 1 unit charge is basically, remember this is 1 unit full charge, has a value of 4.8 into 10 power minus 10 ESU. That is a total charge. You cannot achieve the total charge unless you are ionic, and we are discussing covalent bond. So I would like to say this E value will be less than this. Will be less than this. Rather, it's a fraction of this. Now you ask me, why did I take 10 power minus 10? It's my wish, because I'm staying within the limits. I'm staying within the limits of this unit positive charge. I'm taking 10 power minus 2. Less than this, the whole positive charge. If at all it was ionic, it will never be ionic, because we are discussing what? Covalent bond. It will never be ionic. It is only a shift of electrons from this charge to that charge. So the E will always remain to be fractional. Fraction of the total charge. So if at all to be ionic, this is the full charge, and the full charge value is 4.8 into 10 power minus 10 ESU. And I assumed that let E be 10 power minus 10 ESU. Some people might say, why only 10 power minus 2? Minus 10, you can take 10 power minus 9. Yes, you can take. Why only 10 power minus 10? You can take 10 power minus 6. Yes, you can take. You are welcome to do that. You're welcome to do that. No one will hang you. No one will hang you. Out of this much cloth, 100 centimeter is taken to be 1 meter. That's how people communicate. It is a question of communication. It is arbitrary. There is no absolute, no experimental backing for this. But one thing you must ensure, that the value which you are taking must be less than the total positive charge that is available. You must understand that. Right? So this is how it is. What we are doing is, the product of E into D is dipole moment. And we wanted to communicate with each other. You can't show hands like this much is the dipole moment, this much is the dipole moment. No, you can't do that. So for that we require a unit. And how do we derive a unit is, assume E value is 10 power minus 10 and this 10 power minus 10 have been chosen as a fraction of the total value of the unit positive charge, which is the maximum value of one unit positive charge is equal to 4.8 into 10 power minus 10 ESU, and I have taken the E value to be 10 power minus 10. Right? If E is 10 power minus 10, assume let D is 10 power minus 8 centimeters. That's also an arbitrary value. The distance between the poles, let it be 1 angstrom, that is 10 power minus 8 centimeters. Right? It's an assumption. Then if you put these values and substitute, then mu value will be equal to E into D, where E value is 10 power minus 10 ESU into D is 10 power minus 8, mu is E into D, and the E value is 10 power minus 10 ESU into 10 power minus 8 centimeters. So this will be equal to 10 power minus 18 ESU into centimeters. So you're getting mu to be 10 power minus 18 ESU into centimeters. This is what is referred to be 1 dBi. That's what is referred to be 1 dBi. 1 dBi. So from now onwards, we'll forget everything and we only will discuss about what dBi is. You tell me that I have a molecule in my house which has a dipole moment of 0.2 dBi. Oh, you have 0.2 dBi? I have in my house another molecule which has a dipole moment of 0.3 dBi. So the way we communicate dipole moment is through dBi. And what is 1 dBi? 1 dBi is 10 power minus 18 ESU into centimeters. How did we arrive at this unit? We have assumed that the E value will be what? 10 power minus 10, which will be less than the total charge. This is this much, right? Right? And it's in fact 4.8 times lesser, what we assumed. And we'll assume the distance is 10 power minus 8, and we substitute there, then you're supposed to get 10 power minus 8 ESU into centimeters, and this is what is referred to be 1 dBi. You must understand that, right? So we have a unit now. We have a unit. So what are the highlights, what I'm telling? We are still hanging on to the covalent bond. We are not running away from the covalent bond. We are still at the covalent bond. In covalent bond, you have two systems, homo and hetero. Homo, I have nothing to do, nothing to measure. Hetero, yes, here is the hetero. You can actually see this is shifting towards one of the atoms, which is basically smaller. And when you shift, the charge just develops. When the charge just develops, I'm ready to measure something. I measure something. So when I measure, you can actually see E into D is called nu, where E is the charge that is developed on the as a poles, and D is the distance between the poles. And the product of E into D is called mu. Mu is called the dipole moment. Mu is called the dipole moment. And the question arises, how do we communicate among ourselves? The dipole moment is another issue, right? We can communicate through what? dBis now. So what are the units of units of dipole moment? If someone are asking you, then you tell them that it is dBis. And 1 dBi is 10 power minus 18 ESU into centimeters, you must understand. Right? So that's how it is. So let me very quickly brief this so that we can get into some of the applications of dipole moment. Watch carefully here. This is the heteroatomic system. This is AB. And this is pulled towards that side. So you can actually show the arrows pointing towards B. And this develops a positive charge. So you put partial positive and partial negative. And remember, the unit full positive charge is basically 4.8 into 10 power minus 10 ESUs. So what I've done is basically let the charge be E, and let the distance between charges be D, then mu, which is nothing but the dipole moment, is given by E into D, and the units of dipole moment are nothing but dBis. And 1 dBi, I would like to highlight this. 1 dBi is 10 power minus 18 ESU into centimeters. We get this 1 dBi by substituting E is 10 power minus 10 ESUs and D is 10 power minus 8 centimeters. These are arbitrary values. Arbitrary. I've chosen just like that and substitute here, then you're supposed to get this. And the units of dipole moment are what? DBis. And also I would like to say this is a vector. So I can simply say dipole moment is a vector quantity. Is a vector quantity, you must understand. Is basically a vector quantity, you must understand that. Right? It's shown as a vector. So, if it is a vector quantity, this is what is the concept of what? Dipole moment. Right? And now we will easily communicate on this and all. Now the question is, let us go in for the applications of dipole moment. What are the applications of dipole? What will you do with this? What will you do with this is the issue. Now remember one point here. Remember one point. Covalent bond is basically, theoretically, 100% covalent bond. I'm speaking of 100% covalent bond. A 100% covalent bond is that when the shared pair is exactly at this center. The shared pair must be exactly at this center. Now suppose if shared pair is not at this center and is shifting towards the other side, which are smaller, then I would like to say ionic character is being induced. It is ionic character is being induced. The more the shift of the electrons towards the smaller atom, more is the ionic character into the bond induced. Remember, I'm speaking of ionic character. I'm not speaking of ionic bond. I'm not speaking of ionic bond. It's almost like this, that some males have female hormones more, so they behave as a females. You can see their voice or something like that. Their behavior is somewhat more inclined towards female. That doesn't mean that he's not a male. Of course, definitely he's a male, but he has some female characteristics. There are some tennis players, American tennis players, Williams sisters, where of course they play in the female category, but if you look into their muscles, they are almost like male strength they have. Rather, typically a female must not be having that much muscle as men. But yes, some females have what? Men characteristics. That doesn't mean that it's not a female. Some males have some female characteristic. That doesn't mean that he is not a male. But we can actually visualize these characteristics in each other. So similarly, what I'm telling is basically here is that in heteroatomic system, the bond pair is shifting towards one of the atoms which is smaller. The moment you shift towards a smaller atom, ionic character is being induced. Ionic character is being induced. And more the shift, ionic character will be induced. So what we are discussing here is basically ionic character in covalent bond. It can never become 100% ionic. We are speaking of ionic character in what? Covalent bond, you must understand. Cut it off. Right. So once we know the dipole moment and its units, let us go in for applications. When I say the applications, when I'm taking up these applications, remember that this application is an exam question and you can bank on it and it will come in exam, whatever pre-engineering test or pre-medical test you are writing. Now, what is this application about? Now, first of all, understand, hey, if you are given four options, ask you to choose a 100% covalent bond, then it will be a homoatomic system. The bond between two similar non-metals is 100% covalent. 100% covalent. Suppose if you have a heteroatomic system, the moment you take the heteroatomic system, please understand that ionic character has been induced. It's not ionic bond. It's ionic character is being induced. You must understand that. Once you take a deviation from homo to hetero, ionic character is induced. I'm not telling it is ionic bond. It can never be ionic bond. You must understand, it can never be ionic bond. We are just speaking of induction of ionic character into a covalent bond. That's what we are speaking of. You must understand. Right? So if that is the case, let us take application number 1. Right. So what we are doing is we get into an applications. Now the application part is basically once you shift from a homoatomic system to heteroatomic system, there will be induction of what? Ionic character, which you can't stop. It is only an ionic character. I am not speaking of ionic bond, right? Let's take application number 1 for better understanding. Look here. This is application number 1. This is application of dipole moment. This is application of dipole moment. And remember, using dipole moment, we can calculate percentage of ionic character. Percentage of ionic character in covalent bond. That's application number 1. And this question is compulsory question. You can bank on it. You'll get it in the exam. You will be getting it in exam. So the applications of dipole moment is a sure question in exam. What is this question about? He's telling using dipole moment, we can find out ionic character in a covalent bond. So we are still in the covalent bond only. We are not discussing any ionic bond here. We are discussing just covalent bond. You must understand. What we are trying to tell is, if you are asked to pick up a 100% covalent bond, then if you are asked to pick up 100% covalent bond, you must be picking up two non-metals which are similar. Like for example, this bond between hydrogen and hydrogen is basically 100% covalent. It's 100% covalent. That's how you need to pick up, because it's a homoatomic system, that bond between two similar atoms. You must understand that. Right, once you shift to heteroatomic system, like the case of HCl, this is not similar, these two atoms are not similar, the bond pair will not stay at center, it will be shifting towards the more electronegative atom, that is the chlorine over there, it shifts, and then some ionic character is induced. Its character. HCl is of course covalent. I have no dispute on that. It is of course covalent. Only what we are discussing is how do we calculate the percentage of ionic character in a covalent compound. So I am very consciously writing it. Watch. Using dipole moment, we can calculate percentage of ionic character in covalent bonds. So we are sticking to covalent bond. You must understand, we are still sticking to covalent bond. And how to find out percentage of ionic character is basically this. Look here. Percentage of ionic character is given as mu, that is the mu is nothing but the dipole moment. What mu? Mu is the observed dipole moment. Mu observed by mu theoretical into 100. Now this gives you the percentage of ionic character. Now we wanted to know what is mu observed, mu theoretical, and then into 100. Well, I'll make it simple by telling it like this. Remember, suppose if you're calculating your percentage in your class. How do you calculate the percentage of mathematics? You got your papers, how do you calculate the percentage? Is the marks which you get divided by the total marks into 100. Suppose if the question paper is for 100 and you got 60, so it is your marks which you got divided by the total marks, that is 100, multiplied by 100. So cancel it off and you got 60%. That is how we calculate. Your marks by total marks into 100. So no one will get 100, it's theoretically, right? So similarly, if you want percentage of ionic character, we can actually get through the ionic character through dipole moment. You must understand that. How do we get it? Mu observed by mu theoretical into 100. Now what is mu observed? Mu observed is basically mu dipole moment observed, meaning it is the real dipole moment. Real dipole moment which you actually get through your experiments. You must understand. It's a determined mu. It is determined mu. That is a real dipole moment. That is a real dipole moment. That is the observed dipole moment in a molecule. Observed. It is an observed dipole moment in a molecule. It's something like the marks which you got. The marks which you got. Now what is mu theoretical? Mu theoretical is nothing but, if at all the bond is ionic. It can never be ionic. Assuming theoretically, if the bond would have been ionic, if the bond would have been ionic, then in such case the dipole moment. It will never be ionic. It's theory. It is our assumption. It is your marks by total marks into 100. So it is your marks by total marks into 100. Your marks by total marks into 100. No one can score 100. It's basically your assumption. It's basically your assumption. You must understand that. Right? So, percentage of ionic character in covalent bonds is given by mu observed by mu theoretical into 100. Whether it is mu observed or mu theoretical, it doesn't matter for me. Mu observed or mu theoretical, it has only one formula. And remember that mu is always equal to what? E into D. Mu is basically E into D. You must understand. It is basically E into D. Right? If that is the case, let us put it properly. Let's put it properly. Application number 1. So the applications of application 1 of dipole moment. Application 1 of dipole moment. And remember, what is this? We can find percentage of ionic character. We can find percentage of ionic character in what? A covalent bond. Percentage of ionic character in a covalent bond which is given by mu observed. That is the real dipole moment, divided by mu theoretical into 100. That is the formula. Now what is, if you are understanding what is mu observed and mu theoretical, suppose if you take AB, right, it has shifted here, you developed partial negative and partial positive, let the charge be E and the distance be what? D. This is what is called mu observed. The partial charge E into distance between these two is D. This is what is called mu observed. Now what is mu theoretical? Mu theoretical is asking us, just assume, it is assumption, it can never be, it's theory, it's theory. He is asking us to just assume that this bond is ionic. He is asking us if at all it is ionic, if at all, it will never be. If at all it is ionic, then this will give you full charges. If it is ionic, it is full charges. So this mu into D, mu is again, this is again E into D, but this E is now a full charge. And this is actually a partial charge. You must understand. That's a partial charge. One is a full charge, the other is what? A partial charge. Right? So basically, let me write it properly. Let me write it properly here. Suppose if you assume AB, and this is the charge developed on it, this E into D is mu observed. The E is basically fraction of total charge. Fraction of the total charge. And suppose if this is ionic, assumption is ionic, then if AB is ionic, then it will give you A plus and B minus. In that case, E into D is also mu theoretical. Theoretical, because we are assuming that this is what? Ionic. And this charge E is now total charge. E is total. It's not fraction. If it is fraction, it is mu observed. If E is total, then it is theoretical. You must understand. So based on this, let us see a problem, straight problem, and I want the students to remember this problem because this will be asked in the exam and you can bank on it, right? Look into this. Look into this problem now. I think you understood what is mu observed and mu theoretical, right? It is simply, I can just extend and write it. This is E into D. This is also E into D, but this E is fractional charge, and this is what? A full charge. That's what is the difference. Full charge and fractional charge. And here is a question. The observed dipole moment of HCl is 1.6 dBs. dBi is a unit of what? Dipole moment. The observed dipole moment in HCl is 1.6 dBs. If the bond length is 10 power minus 8 centimeters, find the percentage of ionic character in HCl. Now, percentage of ionic character in HCl, first of all, understand that HCl is what? A covalent bond. And he wanted to find out the ionic character in HCl. That's what is the question. Right? So it is as simple as that. Let us see. We know percentage of ionic character is mu observed by mu theoretical into 100. So this will be mu observed is given to you. So it is 1.6 dBs. So by mu theoretical into 100. So this can be written as 1.6 into 4.8. Sorry, 1 dBi. This is 1.6 into 1 dBi is 10 power minus 8 ESU into centimeters. So 1 dBi is basically 10 power minus 18. That's what we were telling. 1 dBi is 10 power minus 18 ESU into centimeters. So it is 1.6 dBis. So it is 1.6 dBis. This is 1 dBi, right? Divided by. Now mu theoretical. Mu theoretical is assuming that you have a full charge. Assuming you have a full charge. Now if it is a full charge, mu is E into D. So this is nothing but E into D. The E full charge is 4.8 into 10 power minus 10 ESU into the D is given, it is 10 power minus 8. Right, this is the full charge. This is full into 100. So you can cancel this, you can cancel this, you can cancel this. Right, so 1.6 into 100. 1.6 into 100 is basically, it is 16%, you must understand this. That is how the percentage of what? Ionic character is calculated. So it's basically, you are left out with what? Into 100. So this cancels, everything is cancelling. So the percentage of ionic character is 1.6 into what? 100. That is how the percentage of ionic character has been found out. You must understand. So there is some percentage of what? Ionic character in HCl. There is some percentage of ionic character in HCl because H is different, chlorine is different. The bond pair is unequally shared. It's basically unequally shared. So naturally you can expect what? You can expect what? Ionic character in covalent compounds. So the ionic character in covalent compounds can be calculated as an applications of what? Dipole moment, and it is nothing but mu observed by mu theoretical into 100. Whether it is observed or theoretical, the formula remains the same, that is E into D. In case of observed, the E will be fraction of the total charge. In case of mu theoretical, the E will be the total charge in case it is ionic. In case it is ionic, it's not ionic. In case it is ionic, then we must understand that the E is the total charge which you need to put it. It's almost like calculating your percentage in your subjects where you got your marks by total marks into 100. You won't get the total marks, right? That is put in the denominator. If at all you get it, if at all you get it, if at all you get it, then it is something like your marks by total marks into 100. That is nothing but mu observed by mu theoretical into 100. This is your marks. This is the total marks into 100, and this is the problem, and this you get 100% sure in exam. Must understand this.